In the next stage, we will add some tests. These types of games where we have several rules, how the gameplay evolves, we could write good tests. It would be very valuable to write tests for each of these rules. Think about some small snippets of the board where we set up the field, set up the rocks, gems, player, and we play the game in this laboratory and check whether all the rules are following what we wanted to achieve. These can be very valuable. So let's talk about tests. The idea I came up with was to pass in a parameter like something called run tests, and we will turn the same code into a test binary that way. Because these are the functions we want to test. So I want to keep everything all the tests close to it. Again, this is a decision. If it would be a real code, this would be not a single file. But it works. This idea works here. So the first thing we will do that if we are in the run tests, when we compile, we passed in run tests, then we will have a much smaller board. Maybe like this. That's the existing one. Oh, so we will, I think this board is enough to represent all the rules we want. Then at the bottom, where we have the main function, if not def run tests, we can have our, and this will be our test main. So we will have a bunch of functions here like test, layer, leaves, and then here we will call all of these tests, aggregate the results, and print out the final results. How can such a test look like? So the first idea is that we will have full control over the game state. Here in the old screen, we set up a test scenario. The idea here is that there are two rocks, and here is the player, and the player will just move to the right. We see this from the key 3. That's moving to the right, and we set up where the player is. And then after this, we will set up some expectations. So here is the first one. What will happen after the first update? We expect that the player will move to the right, and this rock will turn into be a falling rock, but did not yet fall to the ground. Then we will have two other steps. Maybe together it's easy to see. So the player moves to the right, the rock turned into the falling rock, then the rock falls down, and then at the last step, the rock turns back to the non-falling rock. This is not the representation necessarily, this is only the internal state, how our rules were implemented. And now let's write some tests, some assertions. How can we assert on that this is really what's happening? So obviously first we call the update. Then the main idea is that just do a mem compare. So we compare the state screen, which was written by the update function, and the expected one. And this is basically our assertion. And then we can do a bunch of stuff, checking if whether it was successful. If it's not successful, so the mem compares return is not 0, then we write out in the red color This is very red. State after update is not equal to expected one. And if this happens, we obviously want to see what's the difference. So one way to do this is that we will call the render function on this screen. So we set up the old screen to a value that is clearly not equal to any value on the screen. So when we call the render, everything will be written out, because you know the render is an optimized way. It will print out only the changes. And now in this way we will make sure that everything is changed, and we will print it out. So this should appear on the upper left corner of the screen if we have such a problem. And then we have to follow the game loop. So if this was actually successful, we have to do this and make sure that we are not moving with the player anymore. We have full control over the game state. And then let's now do the remaining ones. So we are just running the update again and making a mem compare against the expected 2 state, and then we are making a mem compare against the expected 3 state, and so on and so on. Now this is a lot of copy paste, so I just wanted to show a way how we can write tests and how this should live in a real code. This should we will probably have lots of macros to generate these kinds of code. And for example, here in this main, which we did not write at all, we could have code like add test, and then we will pass in the test player lives function, and then add test and whatever. We don't have these, so we have to write a bunch of code for this now. But after a pattern emerges, then we can start writing macros. What I like about this is that these tests are very visual. So when we just look at it, we know that what we are testing, and we can eyeball it. Let's write another test quickly. I will just copy paste it in. Then we will go through it. Again, let's just eyeball it. So what we are testing here is that the rock rolls. So here is the 2 rocks and 2 empty spaces next to it. And what we want to check whether this at the first update that this will be turned into a falling rock, the top rock, then it will move to the left, then it moves to the bottom, and then finally it will stabilize in this state with 2 big O rocks. And the rest is basically just this, except there are some small bugs here. And now let's finally write our main function and run the tests against our code. So these 2 variables, we will collect how many tests we run and the final evaluation of those tests. And here is one of the first tests, the rock rolls. Then here inside the main function, we write out in the individual test whether they failed or not, and then we will write a summary as well. So let's add our other tests. Again, this is a lot of copy paste. These should be behind macros. And then this is the summary of all the tests. And as we are using colors, let's be a nice citizen and reset those changes. Okay, I think this is enough. Let's compile it with the flag. So here we are passing in the run tests flag. Oh, it compiled. And let's run the tests. Okay, so what we see that the test player leaves test was successful, but the first test, the test rock false, failed, and especially in the expected 2. So let's move back to the code. So the expected 2 was this state. Let's print out what was the state with the render to see what failed. Let's move this code here, where we just call render at the expected 2. Let's compile it again and run it. And here, well, yeah, this is a bit ugly. We did not clear the screen, but we see enough. Here is at the top left corner, we see the state we got with render. So the problem is that this rock already fall down. We are at the expected 3 state, at the expected 2. It should be here. Let's clear the screen. Now let's move back again, so maybe we can see it a bit better. This was the test player leaves, which was successful. So we got an assertion error here that instead of this state, when we printed it out, when we rendered it, we were already in this state. Now we actually caught a real bug. Let's move back to the update function above. Here is our update function, and especially let's look at the update all elements. So if you remember, we are iterating from the bottom, from the right, and moving to the left, and then next row from the bottom, moving from right to the left. If we are in that state that the rock will roll down, then when we reach that rock, and we will call the handle rocks gems, which will turn that into a falling rock, then in the next iteration, sorry, I was too fast. Let me think for a moment. So the expected one was successful. It got turned into a rock. Okay. Next element, yes, the rock will move to the left, the falling rock. So we are in this case, and the falling rock will move to the left. And then we move to the next step because we are moving from right to the left. And again, we will handle this very same rock. And that very same rock will then fall down. So we basically, during one update, we updated that single rock twice. So this is actually a real bug. If the rock would move to the right, there would be 2 spaces to the right. This will not happen, just because of our decision of how we are iterating over the full board. Now this is a game, and this could be just a quirk. I mean, we could accept it, and just things like to fall to the left much faster than to the right. That could be part of the charm of the game. But let's fix it now. How we can do such a thing? It's usual. We have our state. The screen itself is our state. So we can just introduce a new state that this rock was handled already. But during the representation, we will not print it out like that, of course. So where should we put these? Here, this is the part where we are handling falling rocks and gems, and then we actually start moving the rock or the gem. So here, yes, this is moving it to the left, x-1. Instead of this, we will introduce a new letters for this. Let's call them like a small p, and a small I. I don't remember why I came up with this anymore. Maybe I was ignored, and well, this is the first word that pops up to my mind is permanent, which is not good. I don't know. I came up with these two letters. So after this, when we reach in the next update iteration again this function, we are not handling it. We don't do anything with it, which is fine. We just have to turn them back on to real rocks and gems afterwards. Okay, the question is, where should we do that? Well, I don't want to move here because moving into these functions, the prerequisite for this that we are in a falling rock or a normal rock or gem. But we could expand these, of course, and then handle this case there, or we can just add them here. This is really just a decision. So in the very same iteration, first we will move here, and that will turn those rocks or gems into P and Y. And in the next iteration, we will pick them up and turn them back to what they were. Maybe not the cleanest solution, but yeah, it was pretty fast. Let's run our tests again. And now everything is successful. Let's turn our attention to the render function and finally add some colors. So the very last stage is about rendering colors and animations, maybe. If you remember, I told you that the rendering, I wanted to keep it dumb, and it's pretty dumb. But the representation belongs there. And the way to do this, well, there are many ways to do this. I will basically just take the easiest approach. So what changed? Instead of just going over the screen and just printing out whatever is in our state, what we did before, so this was that line, now we are actually taking a look at what's in there. And if it's a new line, then we print out new line. We probably could handle these cases in the default section. Anyway, it's here now. And for the walls, we came up with these two colors. I basically iterated them in a terminal, just trying out different colors. This is the first place where what you could move out from here, and these could come from a file. But here, this was the simplest case. So we have a different color for the space, for the rocks, and the falling rocks, and I kept the big O and the small o as it is. And I mentioned this earlier. The reason is because I think it just looks good. It's like adding some small animation to a falling rocks. You can see that which rocks are moving because they change shape a bit. And I kept the same for the gems. So they are, if a gem is falling, then it's actually a big S, even in representation. I'm not so sold on that one, so maybe we should actually keep that as a dollar sign, but I kept it like that. Okay, with these changes, let's quickly look at our code. Do I have the? Yes, we are not running tests anymore. So most of this level is empty space. These are the earths. And yeah, the colors are working. Now what else can we do? I was thinking about some animations. One way to... What kind of animations? But I was thinking that we are changing representation and rendering in every loop. And animations could have a different frequency. Like the gem is shining in different colors, but that is not tied to the game loop, because then we will not change it on every game loop, because that would be so fast. So one way to have some tick that survives the loop is like having an unsigned integer here. And we will keep adding to this unsigned integer. Why unsigned? Because this is guaranteed to loop over. The idea is that we will use modulo operator and divide operators to have some kind of longer tick. So currently we have 10 ticks per second, but maybe we want to change an animation only every second. And that way we will look at whether we will first do modulo 10, and then, or maybe modulo 20, and then we will divide it by 10 to get a 0 and 1. So first we map it. We want to map this unsigned integer that keeps increasing to 0 and 1 every second. To change only by every second. It will be more clearer when I write the code. And why unsigned? Because the overflow is well defined. And where should we increase that? Yeah, I think we can do this here. Okay, and here at render, for example, for the gem, we can do something like what should we do? First we do this. Then we divide by 8. So this will be the first version. And then if it's not like that, then we will print it out in a different color. So this is the background color. I don't want to change that. And this is the color of the gem, which is a... I don't know. Let's make a small change to not make it look very ugly. I just came up with this. And let's do this here as well. Yeah, thinking that this. Now I have no idea whether this will work. Of course, nothing works. So I fixed the problems, moving that mapping from every 16th frame. We divided by in 2 places, so it's 1.5 seconds at the moment. It should switch. So we map that big unsigned to 0 or 1, and when we change from 0 to 1 is defined by here basically. And then we, based on whether this is 0 or 1, we switch to different colors. Now let's see whether this works. Well, it apparently doesn't work. Let's make them fall. And now we saw some colors changing. So what's happening? We are running against our optimization. If you remember, we optimized our rendering. If something stays on the screen, we don't rewrite it. When we made them fall, then the falling gems they changed position, so it had to be redrawn. And then we saw that they can change their colors. How can we fix that? Well, we have to turn off this optimization for the gems. That's the only way to do that. Where is our render function? So here the first line is that if state all screen not equals state screen. Well, we have to move this one out of it. And that's the only way to keep that. Okay, let's do that quickly. We are basically destroying our some of our optimizations. Okay, now we moved those two out, and we still optimize the rest of the screen. For example, the border or the new lines, we don't redraw them. We made a mistake. But it was a funny bug. Yes, we also need this line to move the cursor to the right place. And we don't need this one anymore. Yes, now they are moving at the same speed. We could make them to be a bit async. I don't like how it looks. For example, we can play with the coordinates where they are located as well, and add that to the animation as well. Let's try that out. So here, this is a global counter, but we can spice it up a bit with the coordinate. So here we are calculating this here, and instead of that, let's move that inside here. State.count, and let's add maybe both of these coordinates. And here as well. Maybe let's count this twice. Twice as, oh, 3. Just to give it a variation. Okay, let's see what happens now. Now this is funny. I don't know what I messed up, but they are not getting the other color anymore. Let me check the code again. Yeah. I think that the modulo operator has a very low priority. Now this is a bit better. We get some variation and some funny animation. And actually, I don't like that the gems are printed out as S when they are falling. I want to keep the rocks as they are, but not the gems. And that will make our code look better. This means we don't need these lines anymore. Let's make them fall. Yes, I like this better. Let's stop here. Thanks for joining me on this journey. This was a long series. I hope you enjoyed it, and take the code and expand it how you like it, because that's the best way to have fun. Thank you.